Okay, I think we will get started. My name is Steph Daly. I'm the Global Competition Coordinator for Seesaw, so thank you so much for being here. If you've attended some of our other talks today, then you probably know me by now. I am excited to be here for a talk with Yury Dvorkin, who is an assistant professor and Goddard Junior Faculty Fellow in the Department of Electrical and Computer Engineering here at NYU Tandon School of Engineering. He's also part of the NYU Center for Cybersecurity. Before I do continue with my introduction of him, I'll just interject and say that we've got a Q&A tool that attendees can use. So as the talk goes on, you can enter in some questions there, and we will have time at the end for Yury to address some of those. But back to Yury, his research focuses on modeling and algorithmic solutions to assist emerging grid technology, smart grid technologies. And so he'll be talking about a little bit about that today, focusing on urban power grid attacks. And so with that, Yury, I'll turn it over to you.
Thank you, Steph. I hope that everyone can hear me clearly. Otherwise, please do let me know through the chat. I'm excited. I'm delighted to be here today, and thank you so much for attending the talk. And today I'm going to be talking about examining indirect cyber attacks on urban power grids. And I do come here with an understanding that not many people are power engineers, so don't get disenfranchised when you hear something uncommon, because I will present what power grid operation is all about in a few slides, and hopefully it's going to provide enough of background for you to follow along with the rest of my presentation. So the kind of research that I'm doing is inherently very multidisciplinary, because it not only inflicts on two electrical engineering disciplines such as power engineering, but cybersecurity, but it also provides a lot of interfaces that I'm going to be touching on related to policy, related to social sciences, related to economics. And from this perspective, the first message that I'm going to send forward is that this is an incredibly multidisciplinary area. And what I'm trying to do, I'm trying to bridge the gap between the two thrusts of research that we have here at NYU Tandon. The first one being the Power Lab, where we do focus on traditional research topics for that area, such as transmission and distribution operations, electricity markets, integration of distributed energy resources, and energy policy. But more recently, we started looking into grid resiliency, and in particular in cybersecurity, which provided an avenue to focus on this collaboration with the NYU Center for Cybersecurity, which is a far bigger enterprise here at NYU and includes a variety of faculty working across disciplines of electrical and computer engineering, computer science, mechanical engineering, law, economics, and social sciences. So what we're trying to do, we're trying to inform our cybersecurity work by developments in the power grid, and vice versa. We're trying to take the best from the Center for Cybersecurity and see how this domain knowledge can be applicable with proper modifications into the power aspect. But in order for me to kick off the presentation, I really have to focus on this slide, which describes what electric power distribution is all about. And that is a 24/7, 365 operational cycle, where we essentially have one of the largest on Earth industry control system. And typically the power grid is broken down in three pieces. The red piece stands for generation. These are basically large-scale generators. You pick a technology, it can be coal, it can be power, it can be oil, it can be hydro. And basically the red sector produces electricity at bulk by taking advantage of electricity of scale, and then basically it injects it into the transmission lines, which are in blue on this diagram, which uses very high voltage to deliver power from the power plants where it's produced to major electricity consumption centers. When it hits a big city, which is a major electricity consumption center, for example, New York, this power is being injected into the distribution grid, which tends to use lower voltages. And but anyway, this electricity is being stepped down to urban power grid and being delivered to final customers, which could be large industry, On sub-transmission networks, it could be primary customers, which are basically large office buildings in an urban environment. It can be secondary customers, such as our residential apartments. But the important thing is that this is a continuous cycle that takes into account a lot of information and physical exchanges between entities producing, transmitting, and consuming electricity. But with the exception of the secondary and primary customers, this infrastructure has industry-grade cyber defense. So looking at this diagram and recalling the events that happened in various countries, for example, in Israel, Estonia, and Ukraine, we have come to a realization that there can be a lot of attack mechanisms that target directly different elements on this diagram. And because these attacks target directly equipment that is used on the power grid, and whether it is control information or measuring systems of the system, right? We can devise strategy that can describe whether it's weaponized or alterated. From where we stand, it's incredibly important to mechanize these attacks as well. And there is a lot of ongoing research effort in order to minimize their impact of these attacks on potential system operations. But as we know, these attacks have been successful in the past. And even if you take example of the United States, where you would imagine the notion of cybersecurity of the national power grid is taken quite dearly, we have evidence that some foreign actors that we don't know exactly who that actor is, were able to deploy malware and essentially circumvent the security protocols that exist out there. New York Times prolifically published it in July last year. So from this perspective, despite the fact that direct cyber attacks are possible and they are not fully mitigated, the scope of the work that I'm conducting here is a little bit difficult because we are focusing on indirect attack mechanism. So an indirect attack mechanism would be a mechanism that does not target a power system equipment or control of informational system that can take advantage of industry-grade and sophisticated cyber defense means. Rather, it attacks a zillion of small-scale electricity customers that employ high-wattage resources. These resources can, for example, include electric vehicles, thermostatically controlled loads like HVAC systems, or they can include dishwasher and other energy-intensive residential appliances. And it tried to manipulate the way how these resources consume electricity in a way that it creates adversarial conditions for power system operations and essentially provoke system operators to make operational mistakes or to overload the system in such a way that power system operator would have to shed load and curtail electricity services. And the reason why we believe that studying indirect cyber attacks is a worthy exercise is because first of all, when we're talking about these high wattage resources on the customer end, we really cannot use industry-grade cyber defense because typically we are dealing with ordinary people that do not exhibit best and highest cutting-edge industry cybersecurity practices. And from this perspective, that not only provides an opportunity for an attacker to compromise these devices with a relative ease as compared to industry-grade systems installed on the power grid end, but also to execute this attack in a manner which is stealthy to the utility that operates the grid. So another danger that arises across studying indirect attacks is related to the fact that we do have new objectives. Because these attacks are not necessarily executed instantly, they provide opportunity for adversarial learning, basically for an attacker to improve its knowledge of the system and and cyber terrain, and potentially leverage this knowledge to make it attack even stronger. There is also a bunch of human-in-the-loop factors because essentially attacker will have to internalize the effects of customers being interfaces between the devices and the technology. And another important thing that unlike many other attacks that deal with firewalls and brown malwares, this kind of attacks, they can scale and self-reproduce fairly easily. app spreading would be one phenomenon that can be of interest in that particular context. Among studying very indirect attack vectors, we have been able to itemize some of them that are of a particular interest for this study. And electric vehicles is one of them. And the reason why we want to focus on electric vehicle in this particular work is fairly trivial. First, it's a very high wattage resources. So by compromising a handful of vehicles, you get a lot of power capacity to manipulate at once. And at the same time, this technology is becoming fairly ubiquitous. You can find it in different parts of the country. You can find it in big cities. You can find it in rural areas of North Dakota as well. And these devices, they use the charging process that electric vehicle use. It very often relies on the usage of smartphones, and as a result of it, it provides a very convenient avenue for a potential attacker to compromise those charging processes. Another potential and very impactful attack vector arises from the fact that we do have a variety of AC units that operated in bulk across large urban areas, whether it's your individual AC unit in your apartment that you control using a smart thermostat and application on your smartphone, or it's a very powerful and intelligent building level HVAC system that is being controlled from a smart device of a building or facility manager at that particular building. It doesn't really matter because both can be compromised and both can be operated in such a way that it will be barely noticeable by residents of that apartment or a building, but at the same time it will represent a modification that may destabilize the power grid. So if we're talking about if we're talking about a smartphone as a cyber avenue for an attacker to enter high wattage residential devices and compromise operations of the power grid, then we really should think about the future as well, because more and more residential houses in the United States adopt photovoltaic arrays, and very often the management system that connects this arrays to their to the power grid or to their internal energy storage, it's also being operated through smartphones. So compromising a smartphone can provide a convenient avenue to hijack those resources as well. And that becomes a real threat when you deal with photovoltaic arrays in the context of a microgrid. And one example that I have on the right-hand side of this slide is related to the campus microgrid that we have here at NYU. And you can see that on this photo from 2012, all buildings except for those in the red circle are dark. And that is because that is during Hurricane Sandy when the entire lower Manhattan was shut down and only NYU campus was lit with lights. So from this perspective, compromising individual assets that are controllable on the microgrid level with a smartphone can really be potential threats during high-stake events, such as emergency events when you have to rely on microgrid to supply critical loads. And the final indirect attack vector that has not been demonstrated yet in the field of smart grids, but it's getting very promising because we observe that it's being executed in other domains, for example, in transportation, is that utilities that operate electric power distribution systems, they do extensively rely on the use of machine learning and artificial intelligence algorithms to improve their operations. And it's very possible, it's not possible, it's a given fact that right now they're collecting data on different aspects of system operations, including consumer behavior. And one concern that exists across these lines is that one can manipulate this data in such a way that it would lead to erroneous decision-making on the behalf of the system operator. And this myopic and erroneous actions of the system operator would lead to a black or brown out. So taking these four indirect attack vectors into perspective, we, in our analysis, made an observation that as we go from electric vehicles to thermostatically controlled loads to photovoltaic arrays, microgrids, and machine learning, the least sophistication will be required when you work on the attack from electric vehicles. And On the other hand, if you take attack impact divided by attack sophistication, you will realize that with electric vehicles, you get the bigger buck for your effort, because it allows you to compromise tens, if not hundreds, of power capacity per unit. And that is the power density which is rarely achievable with other devices. So therefore, in this presentation, we're going to focus on the indirect attack using electric vehicles, but we do work on all other attack vectors. And I do have several PhD students who are interested in this work. And if you're interested to pursue this conversation, please do let me know. I'll be happy to start this conversation. So the reason why EVs, as I said, you get to compromise a lot of power capacity at once. And at the same time, adoption rates are growing quickly across the country. And one of the most interesting observations is that it's most likely to be the weapon of indirect cyber attacks that does not have the reciprocity potential, because it's ironic that many countries that are vulnerable, many developing Western countries are vulnerable to cyber attacks using electric vehicles and smart vehicle charging infrastructure. But you can see that potential adversaries that may and have the capabilities of these attacks, they don't have this capacity. For example, Syria, Iraq, Iran, Russia, North Korea, these are the countries which have very little penetration of those technologies, so they will not be vulnerable to such attacks. An additional thing that makes these attacks possible is that they proliferate in different forms. They proliferate as residential, communal, and commercial charges, which are under control of different entities. For example, as a utility, I wouldn't be able to control your residential charger, or vice versa. As a utility, I won't be able to, as a residential consumer, I won't be able to report any problem to the utility should I have any. So from this perspective, the danger is coming from the fact that there are way too many different charging devices, and you do have different charging devices, right? And from this perspective, that also imposes different levels of grids on the system, because if we're talking about some primitive residential charging, the capacity is going to be fairly small on the 3 kilowatts. If the capacity is fairly high and it's an industrial charger, then we're talking about hundreds and hundreds of megawatt of capacity compromised at a time. So moving forward, another potential explanation to focus on this cyber attack level is that even if you take Tesla, the most sophisticated perhaps in terms of convenience of control electric vehicle, you will realize that the charging process, and you can see it here, can be set up on your smartphone. And you can really select different features of your charging process. You can set up a time when you want to charge. You can set up rate of charge by when the charging should be done, and so on and so forth. So basically, it provides a lot of flexibility for a user to decide how much electricity and when this electricity will be taken from the grid, or if you have some V2G type of contract with the utility, injected back to the grid. So from this perspective, this capacity can be, if your smartphone is compromised, can be leveraged against the power grid by alternating this charging. But if you look at this infrastructure that we have up here, different types of chargers and the charging app, you can potentially compromise the app and have information about the charging patterns. But in order for you to be really successful, you have to get this information at scale. Basically, what that means is you need to have information about many charging patterns that will help you to build some aggregated understanding of where charging happens, to what extent charging affects the power grid, and how you can alternate these patterns in a way that would impose adversarial conditions on power system operations. And from this perspective, the critical aspect is to get the data from the charging infrastructure and data on the power grid. And you would imagine that this data would be some kind of restricted access data, but as a matter of fact, both smart EV charging and power grid data are openly available. With respect to the charging data, that is related to the fact primarily that the business model of different companies that provide charging services depends on using this information to attract customers. For example, this data can be applied in a variety of charging apps that work as aggregators for service providers. I'll show an example in a few slides. So basically, before I go any further, What I want to emphasize in this presentation is that we do study the question whether EVs and grid data can be weaponized. And I mean, the reason why I present this work is, yes, it can. The answer is positive, right? So the right question to ask is rather how, because if we understand how this data can be weaponized, we perhaps can develop some cyber defense means. But before we switch to this, it's important to answer several questions. First, is this kind of research needed? Because so far, the only benefit of this research is to educate attackers on how to compromise power grid operations. The other question is whether this research is legal. And the answer to this question, yes, it is. And whether this research is ethical. While we can definitely provide motivation and justification to say yes to the first two questions, the third question is a little bit subjective because everyone gets to decide on their own what is ethical or not. But I'm very grateful to the US government that they helped to make this decision for me. And I do believe that it's ethical to do this research because in the 60s, the US government carried out an experiment which is called the Nth Country Study. They effectively committed one of the DOE national laboratories to assess non-proliferation risks. And as part of that, they wanted to see whether it's possible to design an explosive device with a significant military yield using open source and unclassified data and limited tech support. And their answer was, yes, it's possible. It took 3 PhDs and 2.5 years of work to show that. And they were able to come up with a credible design to show that it's possible. Unfortunately, for some reason, I don't know why, they weren't allowed to build a physical prototype. But that's essentially the design and the spirit of the study that we're conducting here, because our goal is to answer the question whether it's possible to design a cyber attack that would take advantage of compromised electric vehicles and public grid and charging data in order to create a blackout. So the first question in our study is to understand whether we get EV data. And as I said before, there is a bunch of charging apps that provide information for different cities on where you can charge at what time, what is the charging capacity, how many charging stalls are available, what is the price, what is the availability, what is the projected availability, and so on and so forth. As any app in the world, this one has certain vulnerabilities. And just about the time we started working on it, one of the companies, Kaspersky, which has very close ties to Russian intelligence community, they basically published a report about certain vulnerabilities in this app. And one of my PhD students used this vulnerability and the app to get this data. So we were able to access charge points data for the entire Manhattan, and we collected information on hundreds of electric vehicle charging stations for a variety of companies that provide the services from ChargePoint to Tesla and so on. Basically, based on this, we were able to get information about charging behavior across different domains, different times of week, different times of day, different types of stations, different types of chargers at charging stations, and so on and so forth. So basically, we were able to use this known vulnerability that has been patched since then to effectively gain the data that we need to design the cyber attack from the end. So from this perspective, the next question that we have to answer is whether we can grid data. And unlike something very small that you can hide away and protect by distance, you cannot hide away a power grid because this information is available in a variety of resources, and you can get a very accurate representation of the power grid topology and parameters. Using Google Maps, you can snatch on the views of transmission lines and locations of substations. You can use IEEE guidelines to recover some parameters of those substations. You can use press releases and technical documentation of utilities. In our case, it was Con Edison. System operators, it was New York System Operator in our case, US Energy Information Agency, and so on and so forth, to collect information about the power grid. Last year, I was given an interview in one of the New York TV shows, and basically they put a location of the substation on a map as well as the direction of the outgoing cables, as you can see here. So basically, using this public information, we were able to recover the power grid configuration, the high voltage configuration of the power grid, in New York, and this configuration is shown with red lines here. And we also were able to map all the charging stations on Manhattan, where the size of the blue bubbles represent the location, and the size represent the density of power charging at that particular location. And that was a very tedious and scrupulous work that required a lot of attention from my PhD student, Samrat Acharya, who prepared this data. So now, basically what we were able to do using this information and some realistic real-life assumptions that we know from our conversation with co-medicine people I used in practice, we were able to get an electrical circuit diagram representing power grid operations in Manhattan. So the rest is fairly simple. What we have to do, we have to essentially marry this data that we obtained from EV charging station and this power grid data on this circuit in here, in order to decide to find an analytical tool that will help us to analyze the footprint of electrical charging on power grid operation. And as soon as we are able to do that, we can possibly design the attack. And the attack that we will design will come in the form of a feedback loop that uses false data injection by means of alternating production charging profiles of electric vehicles. So that looks like a very complex diagram, but let me break it down for you. So whatever you have in pink is nothing else but a very well-known stabilizer that is used for stable power system operations. And the only thing that we do here is basically we add an adversarial feedback to that model. And this adversarial feedback is being set up in such a way that the gain of this feedback can be optimized in a way that depends on the controllable injections of the electrical vehicles. And we managed to do so by solving a pretty simple optimization problem that takes into account uncertainty factors on our ability to estimate the underlying parameters of electric vehicle charging process. So upon completion of this task, we were able to show that it's enough to have 1,000 electric vehicles charging with high power L3 chargers, which have the charging capacity of 100 kilowatts or more, to destabilize the power grid in Manhattan using this adversarial feedback. And when you do have such a level of instability in the system, which we were able to show here on this Nyquist plot, basically the collapse happens within seconds, and the system operator do not have time to react. Their only line of defense is protection relays, which effectively shed the load, which is the outcome highly desirable by the attacker anyway. So in that particular sense, one key question that we have to answer, if it takes only 1,000 Tesla-sized electric vehicles to execute such attacks, why these attacks have not been executed yet? And there are several reasons. First, in general, these cars remain fairly expensive. And there is a lot of literature in social sciences suggested that people who are coming from more affluent backgrounds, they do exhibit better cyber hygiene practices. And from this perspective, while the penetration of these cars remain fairly low and the cars are not prohibitively expensive, but relatively expensive, that implies that their access to people with backgrounds where poor cyber hygiene practices are exhibited are limited. The other important thing is that we don't have L3 charges everywhere. If you go back in here and you will look at the diagram of Manhattan, you will see that only very few charging stations have a very high power density. Mostly we're still dealing with L2 and L3 chargers. So from this perspective, these attacks are plausible, but there are some other barriers, other non-engineering, I would say, barriers that prevent them from happening yet. So in that perspective, our question was, what can we do to reduce the capacity needed to execute an attack? And we play around with a number of factors in these adversarial models, trying to figure out what conditions can be in the power grid so that they will make it easier to execute this attack. And among such things, we were able to figure out that apparently we can reduce the need down to just about 520. That's the absolute minimum of Tesla vehicles that needs to be compromised in order to execute an attack. We only have to manipulate some demand, which happens on a daily basis because the power system demand changes from 1 hour to another. And from this perspective, we're also very able to show that if you properly select or strategically select a bus where you start your attack, it can also attack your attack surface. But the most important thing, and it's shown in the diagram in here, that despite the fact that we do not have perfect error opacity, we can still achieve these results over a fairly smooth and nearly convex attack surface. So from this perspective, that allows for an attacker to use the smoothness of this surface to essentially probe and play, to calibrate attack parameters and execute the attack with the highest strength. So from our perspective, what is important is to understand where this attack can come from. And the most significant answer that we were able to find in our analysis is that this is really a dilettantic kind of attack that essentially every dilettante with very minimal technical knowledge about the power grid or electric vehicles can execute it. So basically everyone can, when they say that engineering is for all, they literally probably mean these attacks, because even a senior level college student can have a lot of knowledge that are sufficient to plan and implement this attack in practice. And that opens the door for a lot of various actors that cannot target the power grid directly, as in the case of Ukraine, Estonia, or Israel, but they can use knowledge they get about the power system, for example, at a college or at an online course. And this knowledge is available in different languages, in Chinese, in Russian, in Farsi. And weaponize this knowledge without any possible way to prevent this attack ahead of time, because there are simply no safeguards to prevent indirect attacks. So from this perspective, one of the key questions here is defense mechanism. And despite the fact that there is a growing realization that such attacks can represent a mortal threat to power grid operations, it's not exactly clear who should be working on it, for two reasons. Those devices that can be weaponized to be used in such attacks, whether it's AC unit or electric vehicle, they are considered as a non-utility assets. They are customer-rent resources, and technically power utilities do not carry any responsibility for what's happening with these devices, even though they will be the ultimate agent that would absorb the effects of such attacks. And from this perspective, obviously, customers do not have knowledge or do not have resources to identify whether they're being compromised or not on their own, at least a general ordinary person. So the issue here is that when it's not clear who carries main responsibility for preventing such attacks, it's very difficult to devise defense mechanisms. Nevertheless, a lot of people are working on it, but the main problem here is that there is no unified cyber-physical protocols, namely utilities and third-party providers and a lot of customer advocates cannot find a mutually acceptable compromise solution. Even in Europe, where there is a lot of effort into standardizing cybersecurity protocols for energy supply, there is no consensus. One of the primary challenges, and that's related to one of the questions that Ed asked earlier today, is to customer privacy, primarily because the way how we consume electricity can be used to infer a lot of information about us. This information can be useful to protect the grid, but at the same time, this information can disclose some private aspects of our life that that many people would not like to share with anybody, including their utilities. So far, the best defense mechanism, without getting into details, is to effectively understand that your ability to maintain and enhance your password hygiene and you exhibit better cybersecurity hygiene in general would be something that would prevent such cyber attacks. So in the spirit of what President Kennedy once said, the best advice I have is that to thwart such an attack, you gotta use your brain, exhibit best cyber behavior possible, and ask what it can do for your country rather than demand something from your country to do for you. One good thing that comes from a theoretical analysis of this attack design, which when we posed in a risk-constrained midfield game, is that the more EVs you have, the more inaccuracies attacker will have to face, and due to these inaccuracies, attacker will not be able to impose a great level of damage on the power system. It may still cause some harm, but the inaccuracies will reduce their ability to do that. So in our case, we do develop our own solution to defend the power grid, and it's based on understanding that we have to timely isolate compromised assets, and we do develop anomaly detection algorithm, which are enabled by machine learning, that will tell us exactly which parts of the grid, or more specifically, which customers should be isolated, because we suspect that they're compromised with electricity. And one of the most important things here is to share that understanding that we can tolerate local effects on the user end, but that's only justified when we have a clear picture and robust performance guarantees on protecting the power grid from global effects of such attacks propagating into over large geographical areas. One of the most important things why we like this separation/isolation logic is because it gives a rise to a lot of business opportunities, and in particularly to providing incentives to electricity customers to exhibit better compliance with cybersecurity protocols. One important thing here is that what we can offer, and that's a scope of our current work, is that in addition to electricity bill, we can introduce a new product which would be called cyber insurance against electricity theft or cyber electricity attack, and that would be something that you can adjust based on your compliance with certain cyber measures. So from this perspective, I just want to say that as I pointed before, it's a heavily multidisciplinary problem. And recently in the United States, there has been a lot of effort to recognize the danger of power grid cybersecurity. If there is one thing that President Trump, should I say former President Trump, did in his 4 years in the White House that many of us will not forget forever, is that he signed the executive order on securing the United States bulk power system. That was definitely one of very few steps in the right direction, because it allowed to secure high voltage transmission grids and secure the nation against direct attacks on the cyber grid. But at the same time, the scope was of this executive order was a little bit narrow, and it completely disregarded indirect cyber attacks on electric power distribution. And therefore, the attacks that I considered in this presentation, unfortunately, are outside of this of the scope of this executive order. On the other hand, President-elect Biden is preparing to ramp up on U.S. cyber defense policies, and he will keep some legacy from Trump administration, including this executive order. So from this perspective, there is a lot of work in this area, and we hope to continue working across this multidisciplinary synergy of electrical engineering, computer science, and social sciences, because this work provides for a lot of interesting extension that can impact life. It might not provide very interesting math, but it will really provide a lot of interesting life implications. And in terms of some concluding thoughts that we're trying to work on is to design incentives to maintain cybersecurity hygiene. We're trying to find a way to properly share risk between users and utilities, basically to delineate the question about responsibility, which party is responsible for what. And we're trying to inform certain changes in the current regulatory landscape, for example, at the level of IEEE Smart Grid community, to essentially help create such a conducive environment for rolling out these changes that would ensure both trade-off between customers' privacy and system security. We also realize that there is a bunch of interesting risks that emerge in this area. For example, similarly to deep fakes, it's very possible to replace a physically accurate model that we develop in this based on the feedback attack, right, into a neural net and use deep learning to optimize your attack strategy. One thing that can be one thing that prevents such attack from happening is a lack of training data, but potentially this data can become available whether through disclosures or somehow else. So we are very concerned that deepfake equivalents will proliferate in this area. And in general, we do believe that the way how data has been treated over the past 10 years, power grid data primarily, opened a lot of unknown yet unknown vulnerabilities, and that will potentially reduce data requirements for attacks of the future. At this time, I'm a little bit over time, but I would like to thank you all for your attention, and I would like to thank my PhD students because it's really their work. I'm just a figurehead to present their hard effort in a probably they would do even better job presenting it at this time. But yeah, so I just want to acknowledge my students and thank you for your time. And we do have several questions. Let me cover them very quickly. Do you have any research opportunities? If yes, how does one get involved? We do have research opportunities. The best way to get involved is to send me an email. That applies, by the way, if you want to be a PhD student in my group, just email me, we're hiring. Have there been cases where the grid was used to attack specific production facilities or individuals or consumer and products instead of the other way around? Great question. I'm not aware of such things. I would imagine that it happened because it happened on the physical level. There were physical attacks on the power grid to compromise a certain manufacturer. For example, that was an attack on one of the substations that supplied Intel factory near Portland, Oregon. So I do suppose that cyber attacks can be used in that reversed way too. Any other questions? Yeah, we have a hand. Someone has a hand. Mustafa has a hand.
Do you hear me, Yury? Can I ask a question?
Sure, go ahead.
Yeah, thank you very much for your great presentation. How about, I have some questions if you have time, actually.
Probably just 2 minutes.
Yeah. Okay. Very quickly. So about the integration of electrical vehicles. So how you could actually propose a machine learning based detector, because it would be very difficult to detect false data injection attacks. I mean, generally anomalies when we integrate the electrical vehicles actually into the grid, because the grid they will be charged, decharged. So there will be jumps in the data actually distributions. I mean, there will be huge uncertainty in the data. So the charge time or the charge time probably will be detected as attack.
Yeah, that's a possibility. But one thing that we observed in the data that we have is that charging behavior is extremely cyclical. So for us, it's a matter of properly training our model, our machine learning model, rather than doing it. Second of all, what we're using for this task is called risk-constrained federated learning for safety critical application, right? And from this perspective, it can also provide a robust performance guarantee against false positive detections. So there is a challenge, as you pointed out, but this challenge is not something that we basically cannot deal with.
Yeah, but please consider that in the smart grid, since it is a dynamic network, we cannot actually rely on supervised machine learning methods. So you will not be able to actually, in the real world, not in the papers, research papers, you will not be able to actually have access to real attack and real attack class on normal data, because you probably will have access to just normal data.
In the field of machine learning literature, this is also an addressed issue. It has not been applied, by the way, in the power system context, but effectively, you first run the classifier to identify a proper training set, given your current conditions, and for different set of conditions, you will have a different training set, and then you will activate different aspects of your neural net. So I do recognize the technical challenge that you're pointing to. There is no doubt that it exists, but there are technical solutions that prevent that from happening.
I see. What about the insider attacks? Because you could, for example, insider threats.
We're not considering it here. here we are not considering insider cyber attacks. We only consider indirect cyber attacks.
I see. What about the contingencies? Because also, for example, if we imagine that false data are injected in the transmission grid, so if there is a contingency in the actually transmission grid, it also will lead to actually huge and substantial change in the data distributions. So how we can actually isolate them and will recognize fraud, distinguish between fraud and also cyber attack to not raise false alarms.
So in this case, large-scale power outages, whether it's a generator or transmission line, they're being recorded. So from this perspective, it's a matter of refining your data set rather than a matter of technical complexity. So it's how you curate data that you use for training your machine learning, whatever tool you're developing. And it's not only specific to the power grid, it's specific to any kind of application of machine learning, from facial recognition to whatever other application of machine learning you have. The rule is, if you have garbage data on the input, you're going to get a garbage outcome. If you curate and refine your input data, you'll get some useful output, provided that you use adequate techniques.
I see. You also said that even senior student actually can conduct such attack, but usually in cybersecurity we say that these kind of attacks are classified as APT, I mean advanced persistent threat, like what happened in Stuxnet or what happened in Ukrainian attack. For example, in Ukrainian attack, they say that the attack has happened 6 months. I mean, the attackers have worked on the Ukrainian electrical grid, the distribution grid that led to actually power outage of 200,000, I believe, around 200,000 power outages. So they have worked on it 6 months before the attack. They started the attack with spear phishing. So how a student actually can conduct such an attack?
And I'll just interject. Maybe your response to this will be the last response.
Okay.
Yeah, thank you. Thank you.
Thank you, Mustafa, for a lot of questions. Yeah, no, that's a cool conversation to keep going. Yeah. In that particular sense, one of the most important things related to Ukrainian attack is that very little we know about it, for two reasons. First, unfortunately, and I'm saying it with a great level of regret, Ukraine is a great European country with a, unfortunately, very high corruption level. So they were assisted by American and European experts in investigating the effects of the attack that happened over there. But unfortunately, what we know is very limited. In particularly, there is no convincing evidence that it was not an insider's job, right? So this possibility was not completely ruled out. And given the overall level of corruption, not only in the electric power sector of Ukraine, but in general in Ukraine, half of their government is corrupt by another country. So from this perspective, we cannot really say what kind of attack was that. That's one thing. What we know for a fact is that the attack was not launched from Ukraine. So attack was launched from abroad. That is a fact which is established and confirmed by several independent entities. And that's what we know, that executing this attack didn't require an immediate physical access. How that was circumvented, we don't really know. Whether the attack was a persistent threat or not, we also don't know, because it could be a very short-term development. So I would be very careful about any conclusions made about the Ukrainian attack, primarily because we don't know to what extent we can trust them. From this perspective, Russia's attack on Estonia is far more representative, because Estonia is another European country that has a more democratic government system, and they're more transparent in reporting the outcomes of their investigation. And they're also part of the European Union.
Yury, thank you so much.
Yeah, you're welcome. Oh, I have one more question.
Sure.
Can you use computer farms for compromised electricity supply? I don't know what computer farms are. Sorry. Yeah, sorry, I cannot answer. I don't know what computer farms.
Maybe if you want to expand on that question, you could email Yury his emails up here. But yeah, thank you so much, everyone, for joining for that discussion, particularly here at the end. Yury, much appreciated with your time.
No problem. Thank you for inviting me. Terrific to have you all, and enjoy the seesaw. Bye.
Yeah. Bye-bye. Yeah, so the next talk, just to let everyone know, will probably start a few minutes late at 4 p.m. Eastern Standard Time, and that will be in the
auditorium, and that is for strengthening diversity and representation in cybersecurity. So hope you can join that as well. Thank you, everyone.
Okay.